What's up, you guys? Welcome to Integration Bee Training for Intermediates, Part 21. In this section, we will be talking about the Gaussian integral. So, some of you guys might have already seen this, but just to recap, the Gaussian integral looks like this. It's usually from negative infinity to infinity, and we get from e to the power of the negative x squared dx. This is equal to the square root of pi. Now, of course, this is definitely an even function from negative infinity to infinity. So of course, if we only have from 0 to infinity, then this would just be the square root of pi over 2. And so with this formula, we can format integrals in terms of the Gaussian integral. And in integration bees, some people can secretly hide stuff within this Gaussian integral. So let's go ahead and get into that. So we have this integral here. Well, what we could just do is we could just do integration by parts. Just do integration by parts. Negative 1 to 0. Well, obviously we're not going to reach to 0 because the integral for this one would just be, let's see, about like negative half e to the power of negative x squared when you do the basic u substitution, right? But then we're left off with this integral. So we pretty much have x over 2 e to the power of negative x squared from 0 to infinity. Plug in 0, that's 0. Plug in infinity. This would be L'Hopital's rule. This is definitely bigger than this. So this all equals to 0. And then we have plus a half of this integral here. Right? And so this answers to the square root of pi over 4. So that's all it is. You just kind of put it in terms of the Gaussian integral, and there you have it. E to the power of negative x squared with sine x plus cosine x squared. So this looks intimidating, but it's actually pretty simple as long as you just know the Gaussian formula, right? This whole thing is just, let's see, it'll just be 1 plus sine 2x, right? We know that. And now the thing is, if we just split it in two terms, this is just equal to this. It's just equal to the Gaussian integral. And the reason is because on this side, sine 2x is an odd function. So pretty much this here, on this side of the term, is just equal to 0 because it's an odd function. So what we have is just the straight up Gaussian integral here. So the entire integral here is just equal to the square root of pi. Okay, so now we're going to get a little bit uncomfortable. Just a little bit uncomfortable here. So this is just, we could just straight up do a u sub, right? We want it in a form of this. But how do we do that? What should u equal? U must equal to x over square root of 2. Okay? And so what that means is that in the du form, we would have a root 2 at the front. And then from negative infinity to infinity. And so now our answer would be the square root of 2 pi. Okay? Alrighty, we're getting a little more into the uncomfortable stuff now. Yes, it's just a bunch of constants, but we just gotta have to deal with it. We just gotta have to deal with these annoying constants. Alright. So, how do we do with this? That's not an e, that's a 2. Well, we can do kind of a loophole log to help us. E to the ln of 2 times negative x squared. Ah, that's a lot better to see it now. Right. For those who forgot the loophole log, I can just show you the process. You do e to the ln 2 negative x squared 2. Right. This is the loophole log, and you put this exponent here at the side. And that's how we get this. Okay. Now that we have this, you can see that we still needed to put it in terms of this in the u form. But what should u equal? What does u have to be? We let u equal x and the square root of ln of 2. Okay? And so now what we have is we have 1 over the root of ln of 2 from 0 to infinity of the Gaussian integral. And now this is just a half of the square root of pi over ln of 2. This would be our answer. So we have e to the negative x squared, but then we have e to the 2x. So we have this out of the way. So what do we do? Well, what we do is we complete the square. Right, if we complete the square, you end up with e to the, so this would be like x plus 1 square. However, we would be needing a, let's see, oh, actually no, this would be x minus 1. This would be x minus 1 square. And we would need a minus 1 plus 1 here. Aha. And so now what we have is just e negative infinity to infinity. Honestly, you could just let u equal x minus 1 and nothing would change. Right? You would just get this still. So now the answer is just e square root of pi. Okay? Alright, we see some square root of x randomly. Just let u equal square root of x. And then u squared is equal to x, 2u du is equal to dx. Go ahead to just dive right in. Let's see, we got 2u squared e to the negative u squared du. We've encountered this before. We know what to do. 2u, you just do integration by parts. Right. And this would be like a negative half of e to the negative u squared. This will cancel out. Right, we know this is going to become 0 because we've done it before. This just becomes from 0 to infinity, e to negative u squared du. We know what this answer is, square root of pi over 2. Interesting, we have from 0 to pi over 2, and then we have e to the negative secant square. Interesting, right? Well, because of the secant square of x, this kind of gives us a suspicion that we might need to let u equal tangent of x. And that's actually not that hard to see. We could just, this is e to the negative 1 plus tangent square, right? And then if we perform the u substitution, we get 0 pi over 2 at the right hand side of pi over 2. If we plug in tangent of pi over 2, this is infinity. So that actually works very nicely. So now we have negative 1 plus u squared. And now we have 1 over e, 0 to infinity, e to the negative u squared du. And so now we know what this answer is. This is the square root of pi over 2e. Okay? What on earth is this? This does not look like a Gaussian integral. This looks like something else. So what do we do if we just randomly see an ln of some function? We can try experimenting. Let u equal ln of 1 over x. Then e to the u is equal to 1 over x. And then this becomes e to the negative u is equal to x. Negative e to the negative u is equal to dx when we derive it. Okay. So I see, let's see. If we plug in 0, that's infinity. But we're going to use the negative sign to switch the bounds. 1 is 0. So we have the square root of u of e to the negative u du. Huh. This looks familiar. So if you remember this integral here, this is pretty much we just do another u substitution. Let w equal the square root of u, and then you just get into a Gaussian integral. So we've done this integral before. We know that this is equal to the square root of pi over 2, just by doing another u sub. Pretty much the fastest way here would just let u equal the square root of ln of 1 over x. This whole function pretty much. Okay? So, of course, our first instinct is to let u equal ln of x. And what would this give us? This would give us e to the u du equal to dx. Don't know why my marker did that. And then, now this would give us negative infinity because the left-hand side 0, and then ln of infinity is infinity. There you go. And so now we have e to the negative u square plus u, technically, because of the e to the u du. And now we have this. Here, you have no choice but to complete the square. So, we'll go ahead and complete the square. This actually becomes, this would be u minus a half square plus 1/4 du. Right. You get like square root of e with square root of pi, pretty much. Yeah. So the answer here is just going to be square root of pi, square root of e. I think writing it like this is a beautiful way to write it. So yeah, this would be our answer. Let u equal the square root of 1 plus ln of x. Then we get u square minus 1 and e to this whole thing. Right. And then let's see. Yeah, this should equal to x. And then if you derive it, you get 2u e to the square minus 1 dx. Put du there. So now this becomes, plug in infinity, this is infinity, plug in 1 over e, that's 0. So now we have u, 2u square actually, e to the u square minus 1 du. But then we have x here, e to the u square minus 1. Is that right? U square, e to the u square. Oh, I'm sorry. This is x squared. This is x squared. So we still have another one of these. Okay. I was tripping for a second. All right. So now in that case, we are good. This is 2u squared e to the negative u square plus 1, technically, or I'll just put e. Let's put e right here. And we've done this integral here as well. Alright, we kind of already done this integral. This is just going to equal to e square root of pi over 2. Right, you just do integration by parts and you're good. Okay. Okay, this looks weird. This looks like it doesn't converge at all. So what on earth is this? Let u, now this is going to be a little weird, but just trust me on this, okay? It's going to be very weird to see. But if you let u equal 1 over x, and the reason why I want to put this is because this is being squared. And so just out of curiosity, I want to see what this does. And of course du is equal to negative 1 over x squared dx, in which we can just replace with u squared. Okay. So then we have plug infinity. Oh well, we have this negative here. To switch the bounds, so we have infinity 0 here. Okay, nothing changed. We have 1 minus e to the negative u squared like I wanted, but then we have u squared at the bottom because of the du. Right? Because this 1 over x squared, this is technically u squared. And we just kind of like go like this. And this is what we have. Okay. But now what? What do we do here? Integration by parts. If we go like this, 1 over u squared. And this is negative 1 over u. When we integrate, and then here, when we derive, we get 2u e to the negative u squared. Then, what you have is pretty much 1 minus e to the negative u squared over u. And obviously, if you just take the limit, this is just going to equal to 0. So this is just 0. And then the rest here is going to give us 0 to infinity e to the u squared, e to the negative u squared du. And so now what we have is our answer is just square root of pi. There we go. Be very careful with negatives, especially when you do integration by parts. Be very careful with negatives. Okay? What on earth is this? This looks cool. This looks very freaking beautiful. But it is also very awkward to see. Well, let's not hesitate. Let's try doing like a power sub just to get rid of this fraction, right? Let u cubed equal x, and we get 3u squared du dx. Then we would end up getting what? E to the negative u squared, and then we get u negative 2, right? And then we also have 3u squared du. So this cancels out. Ooh! It's 3 times e to the negative u squared du. It was actually pretty cool. So the answer is just 3 square root of pi over 2. Okay? Don't freak out. It's 3 halves. ln of 1 over x, that's how you know this is going to be a Gaussian integral. That's just how you know it's going to be a Gaussian integral. It's just the square root ln of 1 over x. This is how you know it's going to become a Gaussian integral. So let u equal the square root of ln of 1 over x. U square, this is going to be negative e to the u squared, right? This is equal to x, and then negative 2u du equal to x. There we go. So now what we have is, let's see, plug in 0, get infinity to 0, just utilizing this negative, 2u e to negative u squared, u cubed, so that's technically what we have, du, so it's 2u to the power of 4. Interesting. We would have to do integration by parts. But like, I don't feel like doing that. But we have to anyways, because it's just how it in speed integration is. 2u for e to the negative u square. Okay. And then we have 2u cubed, not 2u cubed, 8u cubed. And then 24u squared. Oh no, we can't do that. Ooh. What am I doing? No, we can't do that. What am I doing? 2u cubed. Oh no, I'm getting lazy. Let's see here. Actually, let me bring in the 2 here and have this be u cubed. Then we get negative 3u squared. And this would just be this. Oh, well, what's the negative? We need to have the negative. If you go like this, it's just going to equal to 0 when you plug in 0 and infinity. The limit is just going to equal to 0. So this whole integral is just going to equal to this. And I mean, we've done this before. We know what this is. This portion here, this integral was root pi over 4. What is this? Now this looks very awkward, but let's calm down. Let's calm down and let's just kind of see where this takes us. Right? Let u equal square root of x minus 1. Then u squared is equal to x minus 1. 2u du is equal to dx. Okay. So if you plug in infinity, plug in 1, it's 0. Okay. So we have 2u du. Then we have e to the x, which is u squared plus 1. And then we have u here. This cancels out. Okay. Huh, what is this? This is a Gaussian integral. Minus 1. So we technically have 2 over e. So our answer would probably just be square root of pi over e. And that's it. Oh god, we have a hyperbolic trig function, and we have this half alone here, which does not look convergent, but this surprisingly does converge. So what do? How do we do with this? Well, the easiest thing to do is whenever you see some weird hyperbolic with this inside, turn it into exponential form. So let's go ahead and turn this into exponential form. We'll just leave this as a half. And here we have e to the negative x squared. This would be ex squared minus e to the negative x squared over 2. Right? And so now we can just sort of simplify this further. I can already see that with this and this, with the half, this is going to get canceled out. So I can already see just straight up that this is just going to be a half e to the negative x squared dx. Oh, no, it's not. Be careful. Ooh, be very careful. No. You have this. Let me color this, actually. You have this and this. They're going to add to each other negative 2x squared dx. Be very careful. Be extremely careful. Okay? Don't go too fast. Okay. Now, what do you see? Now we see if we let u equal square root of 2 of x. Right? Now this is 2 over root 2. Infinity to infinity. E to the negative u squared du. And so now our answer is root pi over 2 root 2. This looks crazy. Like, this looks very weird and intense to look at, right? Like, you're just staring at this, just menacingly, like, what on earth is this integral? So, let's calm down. Let's just calm down. whenever you see a function over to the power of a function, we always do a loophole log. So that's like the first thing to do, and then see where our ideas flow into. So e to the ln of all of this. So it would be like this, ln of x. And this is just exponentially. We can simplify this into, let's see, this would go into negative half ln squared. Does this look familiar? Does this look familiar? Remember this? And that it had like a very beautiful answer. It was like root pi over root e. Do you remember? So something like that. That's not going to be the case, because if we let u equal ln of x, ln of x, what's going to happen is we end up with, let's see, negative infinity to infinity, right? Because the right hand side of 0, plugging it into ln, you get negative infinity. And we'll be left off with e to the u, because that's our du, and then minus a half of u squared du. And then here, you have no other choice but to complete the square. It's going to be nasty, but once you get used to it, I'm used to it at this point, this is just pretty much a half. And then this would be like u minus 1 squared du. And so what we would do is let u equal u minus 1 of root 2. Right, so w is equal to u minus 1 over root 2. I know, nasty, annoying constants, but you'll get used to it. This is square root of e. And then root, okay, so we have square root of 2e at the front, and then we have e to the negative u squared, to w squared, dw. And now, our final answer is the square root of 2 pi e. A very satisfying answer. Okay. And that's it, and that was our last integral. So, Gaussian integrals, knowing just that one formula, and then putting integrals in terms of Gaussian integrals. Alright. The most annoying part that you have to get used to is just probably completing the square, because I think when people go fast, they kind of tend to miss on completing the square with Gaussian integrals, because constants will always be messy, and you just have to learn how to sort of deal with that quickly. Okay? So I hope this technique is helpful, and I'll see you guys in the next section.